Can record. All right. Well, as Enrico said, let me just encourage people to interrupt and ask questions during the talk. It's supposed to be spontaneous, but if you don't want to, there is the raise hand feature. Well, I think, yeah. If you put like, dislike, or clap, I will probably see it. But anyway, you should feel free to unmute yourself and ask a question. So, all right, so we'll kickstart the meeting with Enrico telling us about building a boostless bootstrap.
Okay, yeah, thank you very much. So this is the title, Building a Boostless Bootstrap. Hopefully these words will become clear during the talk, and it is based on a few papers that I had this year. The first one in collaboration with Daniel Green, the second one together with David Stefanizin and Jakob Super, and the last one with Sadra Yazayeri and Harry Goodhue. This third paper was supposed to appear last Friday, and then it was delayed, and then it was delayed again. So I posted the preprint on Slack on the channel 1, if you guys want to take a look during this talk and during the subsequent discussion. And it's based on a fourth paper by myself that hopefully will appear in the next few days. So first of all, I wanted to thank my collaborators in my group here at the University of Cambridge, Sadra Yazayeri and David Stefanizin, who are postdocs, and Sadra is about to leave and move to Paris to work with Sebastian, and Harry Goodhue and Jakob Super, who are PhD students and contributed to the papers that I mentioned above. So here is the summary. I'll start with a discussion. I'll be very brief because I think a lot of people here share the interest in the study of cosmological correlators. And then I'll try to define what the observable is. And once I define it, I'll show you how the boundary observable, meaning correlators at future infinity, can be derived without any reference to the Sitter boost for the bispectrum of massless scalars and tensors. And then I'll discuss how to go beyond the bispectrum using a newly derived set of equations, which we named the cosmological optical theorem, that encode the implications of unitarity on the space-like boundary correlations. And then I'll end. So just to be brief with the motivations, many of us believe that cosmological surveys measures quantum correlators in a theory involving perturbative quantum gravity around quasi-Sitter, and we would like to understand these observables as well as possible. However, there are many models of the early universe that differ in terms of the number of particles, spectra, interactions, mechanisms, and many of these models are degenerate with each other because they lead to the same boundary observables. And the problem is that we cannot observe the bulk evolution, but only see the boundary value of correlators at future infinity. And so the roadmap for this talk is to focus exclusively on these well-defined observables in a theory of quantum gravity, namely the future asymptote of correlators or of the wave function of the universe equivalently, and try to stick to this boundary perspective without making assumptions about the bulk evolution that generates these observables. And this is related to and influenced by many other papers that have come out recently, and we will hear much more about this approach from different perspectives and different progress that has been done over the years by other talks. In particular, tomorrow Hyde and Lee will talk about it, and there were several pre-recorded contributions already on YouTube by many of us. And so I think this will be a topic of more discussion during this workshop. So let's start with the symmetries of cosmological correlators that I wrote in collaboration with Daniel Green. So first of all, I want to define what it is, the thing that we want to measure. And so I'll prove two theorems that help us make this step that I think are very foundational to define what the goal is of this research direction. So theorem 1 will demonstrate that the correlators of curvature perturbations are uniquely characterized by their soft limits. And I'll explain this more in detail. And theorem number 2 will show that the only theory of curvature perturbations that is fully invariant under the Sitter isometries is the free theory. Both of these theorems, 1 and 2, are only valid, they assume a single clock cosmology, but make no further assumptions about the particle content or other interactions. So as long as it is single clock, you can have 32 fields with arbitrary interaction, arbitrary masses or spin, it doesn't matter. These theorems still apply. So theorem 1 for me really defines what we care about. So when we consider particle physics, we don't need quantum field theory to define the observables. Amplitudes are well defined as long as you tell me what goes in your collider and what comes out. And to define that, you attribute certain quantum numbers or certain states, for example, the momentum, the spin, or the charges. You give it a name, maybe you call it the particle, and you tell me which quantum numbers go in, which quantum numbers come out, and that defines an observable that you might try to understand. In cosmology, however, we do not do that traditionally. Rather, we usually write down a field theory Lagrangian, which is a certain gauge. Within that gauge, we define the variable that we care about. We do some calculation, and we obtain correlators. But if we insist on taking a boundary perspective and describing observable without any reference to their time evolution, we need to have a better understanding of what the observables are, a better definition. In particular, in some sense, at the practical level, if I give you a correlator and I tell you, look, this is a bispectrum, how do you know of which field it is a bispectrum? At the extremely practical level, how do you know if it is a bispectrum for zeta or zeta twiddle in this slide, which is zeta plus zeta squared plus something else? Only one of these things is what we actually measure in the sky in cosmological service, so you need to be sure that you choose the right one. So, the question that I'm asking is, what are the quantum numbers of zeta? And we answer these questions with the following theorem, and the answer lies in considering the soft theorems of these correlators. So in single clock inflation, all correlators that involve curvature perturbations on comoving hyperslices satisfy certain soft theorems, meaning that their behavior as one of the momenta in the correlator goes to 0, is much smaller than the other two, is fixed by lower endpoint correlation functions. And the famous one is the one originally derived by Maldacena, in which the bispectrum is fixed by the power spectrum square. These soft theorems can be thought as consequences of the existence of non-linearly realized symmetries. So if I define D to be the dilations in the sitter, which on the boundary generate scale invariance, I can think of a nonlinear version of it, which I call D nonlinear, which is basically a dilation, but there is on top of it a nonlinear shift by some constant. Equivalently, I can define the nonlinear cousin of the sitter boost, which I call K nonlinear, which is almost like a boost, but on top of it, in front of it, there is a nonlinear shift. What's important about the symmetry is that the symmetries apply to every single field model of inflation, irrespectively of whether the space-time or any other background respect the sitter isometry, a fact that was nicely stressed and appreciated by Kurt Interbichler, Lam Hui, and Justin Khoury a while ago. So the symmetries have to be there irrespectively of the sitter. Given the symmetries, then you can prove.
A question here already.
Yes.
Yeah, can you go back to the previous slide? So does this assumes asymptotically the sitter, or it could be any space-time, not accelerating?
It has to be accelerating, because here what I'm doing is that I'm dropping the time derivatives. So I'm assuming that correlators stop depending on time in the future. So I'm thinking an accelerated space-time. So I want W.
Power law, power law, accelerating by power law?
I think would be fine.
But it's not going to have the symmetries you indicate here if it's power law.
Why not? The symmetries have nothing to do with the isometries of the space-time. They can be interpreted as large diffeomorphisms, meaning specific form of diffeomorphism that do not die at infinity. And in the same way that large gauge transformations in QED exist as global symmetries, these things exist as global symmetries. It is the analog, if you want, and is not related to the isometries of space-time. It's just a diff, but a specific diff that survives at the boundary, and so that's why we get to talk about it.
But you want this diffeomorphism to survive at the boundary, right? So if you have a power law, let's say space-time, even at the boundary, you're not going to have that. So you need at the boundary, you're going to have, in a sense, this is going to break the translations in spatial conformal transformations if it is accelerating but not de Sitter-like.
Yeah, exactly. Spatial conformal transformation has nothing to do with this. This applies to any FLRW, and the derivation is based on any FLRW, and it follows the concept of adiabatic modes, which can be easily and straightforwardly derived for any FLRW without any assumption of A, except for the fact that it is accelerating, so things asymptote constant. But it is not related to de Sitter. You can do this for W equals minus 2/3 if you want, and it will be the right result. I'm happy to give you very
yeah, maybe we discuss it after. Yes,
in detail, but I think there are like a good dozen, if not 2 dozen, of people that have written papers on this, and I think it's clear that it relies just on large diffs on FLRW rather than de Sitter.
Enrico, is that true even for the third symmetry, the linear dilatations?
No, the third symmetry is not related to the sub-theorems, but I put it here because it's what I'm going to assume throughout this talk. I'm going to assume that everything is scale invariance, and I'll mention small departure from scale invariance later on. What I said should apply to the d nonlinear and k nonlinear.
Okay.
But in the talk, I will assume also scale invariance, at least approximately. Thank you.
All right.
Just can I ask just a simple question, because I'm to deconfuse myself. What are the conserved charges associated with these global symmetries? Is this a sensible question?
It is not clear to me the answer to that question. I'd be happy to leave it for a discussion after the talk, since it is not really the focus here.
Well, can I say formally that charges won't exist because they're nonlinear symmetries? If you like, they're spontaneously broken.
I mean, usually you can still define some divergent charges and use it in commutators.
Yeah. So the commutator of the charge with local operators exists, but
Yeah.
the charge itself formally doesn't exist.
Yeah. I mean, formally the charges, for example, the charges of d nonlinear, it's just the conjugate momentum to zeta times a constant, which generates this transformation, but it's not useful really when you do the integral, but rather just as a generator of this transformation. Very good, very good. So I'll keep going because there's a lot more to come. But please bring back these questions to the discussion, and we can get more to the bottom of it. So what I'm trying to make a point here is that each one of these transformations fixes, all of them together fixes all possible field redefinitions. So if you want to do a field redefinition that doesn't depend on derivative, that's not allowed by d nonlinear. If you want to do a field redefinition that has inverse Laplacian, that's not allowed by this specific form of k nonlinear. And so because of this, we obtain a theorem that says that a given correlator is a correlator of zeta if and only if it obeys all the single clock soft theorems. So now if I give you a correlator, you don't have to ask me, oh, what is the correlator of? You can just check. Does it obey the soft theorem? Yes, then it's a correlator of zeta. No, then it is not. So this defines what it is that we want to compute. The correlator of zeta as measured by cosmological surveys in single field inflation. Very good. Now that we have a definition of what we care about in single field inflation, we can move on to specifying some of its properties. And clearly a key player here are the Sitter boosts, which are an extremely powerful set of symmetries that when linearly realized on correlators can lead to an extensive set of results just based on symmetries. However, as we know well from the phenomenological models, we get large non-Gaussianities only when there is something that provides a large breaking of the Sitter boost, such as, for example, in models of small speed of sound, when CS is much smaller than 1, then you get non-Gaussianity, which is of order 1 over CS squared, and it is large only when CS is much smaller than 1. And so you might wonder whether this is a coincidence, and in fact it is not, but rather it's a consequence of a general theorem that says that if you have special conformal transformations, or if you have the Sitter boost, you cannot get any interacting theory. Only the free theory has that symmetry. And I'm going to show you a sketch of how that, for correlators of zeta, of how that theorem is derived. And this theorem makes no assumptions about spectrum of particles, interactions, their mass, as long as the theory is single clock cosmology. So let's list all the symmetries that we have. We have all the isometries of the Suter space, translations, rotations, dilations, and boosts. Now all of them linearly realized. I mean, you might try what if they are linearly realized. And on top, we have these two non-linearly realized one, which as we just discussed in theorem 1, define what we mean by the correlators of zeta. And now this set of generators is just too much. The algebra corresponding to this is an infinitely large algebra, has infinitely many generators. And you can see this by commuting K with K nonlinear, you get something new, which I call V, and then you commute V with K and you get something new, and so on and so forth. And there are infinitely many new generators. And they all correspond to shifts of zeta by a polynomial in X of arbitrary order. So you might already guess that there's going to be no theory that is invariant under this except for the free theory. And that's indeed the case. And we prove this more formally by writing down the operator product expansion of zeta, subtracting from it the value that we would have for the free theory. And whatever is left, we call it interactions. So Cn times On, where On are some operators and Cn are coefficients. By acting with the infinitely many generators on the left, you always get 0. So you have to get 0 on the right. And this implies that all the Cn's are 0. And so the theory has to be the free theory, in the sense that its operator product expansion is that of the free theory. So the implications of this, yes.
Enrico, I have a question. Can you give more explicit description of this theorem?
Yeah.
In the sense that, so you first you gave this example. I mean, first you said that the interactions are weak unless we break the zeta isometries, like having CS larger than 1. But weak is different from free.
Absolutely, yeah.
You're saying something is stronger. Can you tell me?
Yes,
like,
thank you for asking. I wanted to say it, but I didn't want to spend too much time. The FNL is equal to 1 minus CS squared divided by CS squared. When people say FNL equilateral orthogonal is 1 over CS squared, they just are already in the limit of CS small. Actually, the expression is 1 minus CS squared over CS squared. So when CS is 1, it's not small, it's literally 0.
Sorry, but what about the, I don't know, the 4-point function coming from the graviton exchange? What about, or the epsilon, or the eta 3-point function?
Very good. So here we are working in the slow roll limit, in which we neglect slow roll corrections that invalidate both exact invariance under dilations and exact invariance under special conformal transformation. So in that limit, all these interactions have to vanish. So this is derived in the limit in which you're neglecting all slow roll corrections and you are in the decoupling limit. So epsilon to 0, eta to 0, eta dot over eta to 0.
But what are the 4-point function? Doesn't it also vanish? The one graviton exchange 4-point function?
Yes, yeah, that has epsilons in it. So
I'm not sure.
Both the contact one and the exchange one have epsilons in them, and so there's low roll suppressed. Unless you break it.
Sorry, but if I imagine, if I just have the scale test, the scalar field in the zeta, doesn't it interact via the exchange of graviton?
That's correct. Yes, test scalars do not obey this theorem. What was essential in this theorem was invariance under D nonlinear and K nonlinear. So any test scalars, you can write down as many interactions as you want, and they will be large within the zeta. But when you say that this is not a test scalar, this is zeta in single field, and therefore is invariant under D nonlinear and K nonlinear, then you get the theorem out. So indeed, you're right. For a test for a spectator scalar, the assumption is violated. So
I thought the 4-point function that comes from the graviton exchange is basically the same as the one that you get for a test scalar.
I mean,
just do use your old-fashioned inflaton phi to one graviton exchange phi.
I think the issue is, what do you mean by going to 0 or not? Because you have to divide it by a certain number of power spectra. What I'm trying to say is that when you divide it by the power spectra of zeta that have epsilons in them, then that thing has an epsilon and goes to 0.
Well, in a sense, power spectrum of zeta is not even defined in the de Sitter limit.
That's correct, yes. So this result here that I'm discussing is at the technical level is derived in the decoupling limit, in which we take epsilon to 0 and therefore are allowed to neglect interactions with gravity, because the solutions of the constraints all become trivial.
Okay. Thank you.
Thank you very much. I'd be happy to chat more about it.
So these D nonlinear and K nonlinear are derived assuming that N and I are 0 in the line elements.
That's correct, yes.
Okay.
Otherwise there are terms, but for simplicity, yeah, we didn't account for that.
All right.
But as you're all pointing out, surely if you have Zlorod parameters, then you can get something which is proportional to a Zlorod parameter. And so it's not going to be 0, but we're pointing out that you're not going to get something which can be parametrically large. This does not apply to multi-field models. So it was essential to use the soft theorem. So in multi-field models, nothing that I'm saying applies. Very good. So in the interest of time, I'm going to move a little bit ahead and take this theorem 2, this result, as a motivation to try to understand the observables that we have, namely the boundary correlators or the wave function of the universe, without invoking the isometries of the Sitter space, because in cosmology they are generically broken. They are broken during inflation, and in particular they are broken by a large amount during the phenomenologically interesting models in which you get large non-Gaussianity. So can we do that? And so in the next 20 minutes I'll try to convince you that there is a way to do it without ever invoking the Sitter boosts. And I'll be able to do that only for the bispectrum, but then in the last part of the talk, I'll show you how you can go to higher point functions. So this is going to be a boostless, what I'm going to call a boostless bootstrap, which is similar and very strongly influenced by the ideas of doing a bootstrap in the Sitter using all the isometries of the Sitter, but it's going to take into account the fact that many models that we care about are not symmetric under boost, and therefore I would like to still understand those models, so I cannot use boosts from the get-go. So I'm going to name this idea a boostless bootstrap. So the goal is to find a set of rules that only apply at the boundary, are only functions of the observables, and the solution to those rules are all the possible correlators. I'm going to be able to do that at the level of the bispectrum, at 3 level. I'm going to use general principles and symmetries. And the main trick, as suggested by this drawing, is the amplitude as a lever, as a point, and lift up the amplitude, which we understand well, to the full correlator. And I'll be able to derive all bispectra, not necessarily the Sitter invariant, for massless scalars and graviton. So let's see. The set of rules is the following. There are 6 of them. I'm going to go through each one of them one by one. Some of them are trivial, some of them are more interesting. So let's get going. The first one is trivial, just translations, rotation, and scale invariance, which I will assume all to be exact. And so that tells me that I can always write down the bispectrum for fields of any spin, massless, as the product of something that depends on the polarization, which must be contracted in a rotation invariant way with momenta, times whatever is left, which must be only a function of K1, K2, K3, the norm of the 3 momenta, which I'm going to call the trimmed bispectrum. So there's going to be a polarization factor, and whatever is left, I call it the trimmed bispectrum. It's almost the bispectrum, but I take out all the polarization factors. For a scalar bispectrum, there is no polarization factor, and the trimmed bispectrum is the same as the bispectrum. Scale invariance tells me that the trimmed bispectrum has to scale with K in a specific way, which is -6 minus whatever powers of K appear in the polarization factor. Rule number 2, it's that we are working at 3 level in the Sitter space. And so the trimmed bispectrum must be a rational function of the norm of the momenta. That's to be a polynomial divided by another polynomial. This is equivalent to say that we're working at tree level and that the mode functions that we have are de Sitter mode function. Notice I'm not assuming full de Sitter invariance for the interactions, but I do assume that the mode function are the de Sitter mode functions. There is one exception to this, which is an important one, which are logs, and I'll discuss them later. Rule number 3 is the powerful one, is the amplitude limit. It has been noticed already almost 10 years ago by Guy and Maldacena, and then by Raju, and it has been elaborated upon in the past few years that correlators have a pole when the sum of all the norm of the momenta vanishes. So I'm going to call that the total energy pole defined by KT equals 0. And the residue of that pole is related to some amplitude. In this recent paper that was supposed to appear today and that we posted on Slack for you guys to see, we proved this result in a rigorous way using the informalism, and we derive a formula which has all the factors of 1, 2, I needed to get exactly the right result. And so this formula says that the bispectrum, when KT goes to 0, is some numerical factor in front, where H is the Hubble parameter, times the real part or the imaginary part of the amplitude, depending on the value of n or p. So it's not just the amplitude, of course, because the correlator is a real quantity and the amplitude is complex. And the order of the pole is p, and this p is fixed. P is fixed by dimensional analysis and scale invariance. And I can easily derive that the value of p is equal to 1 plus the sum over all vertex, each one of the vertex in the diagram that leads to this correlator, of the dimension of that operator minus 4. For the contact bispectrum, there is only one vertex, and its dimension is 3 plus the number of derivatives. So the 3 plus 1 minus 4 cancels. So p is only the number of derivatives. So this is really just a Taylor expansion in the effective field theory in the number of derivatives. P equals 0 is no derivatives, p equals 1, 1 derivative, and so on and so forth. This is going to be very powerful in the bootstrap that follows. Rule number 4, it says that if you compute the bispectrum of 3 identical fields and the polarization factor is symmetric, then also the trimmed bispectrum has to be symmetric. And now we use an important theorem from the theory of symmetric polynomials that says that any symmetric polynomial can be written in terms of elementary symmetric polynomials. And for 3 variables, you only need 3 of them. They're written here. The first one is a good old friend, is just k total, k1 plus k2 plus k3. And then there are 2 more elementary symmetric polynomials that I'm going to call E2 and E3. And they're just the product of all possible pairs and triplets of momenta. What's important is that the bispectrum can be written in terms of these things in a unique way. It's going to save us a lot of work when we write the result. So even though this is just a silly change of variables, it's actually in practice extremely useful. Rule number 5, locality and the Bunch-Davis vacuum. This is also very powerful because it fixes the denominator in this rational function. It says that the denominator can only be either k total to the power p, as we have seen before, and that's the total energy pole, and a factor of E3 cube, which is k1, k2, k3 cube. And that just comes from the normalization of fields from a bulk perspective. But from the boundary, this is just defines the poles of this object. This is very powerful because by fixing the denominator, the numerator is just a polynomial of a fixed order, and you know the order. So now the whole computing a correlator just boils down to writing down a polynomial that has a certain number of free numerical coefficients. The only thing you have to do is fix those coefficients and you're done. Any deviation from this rule implies either that you consider non-local interactions, for example, interactions with an inverse Laplacian, or that you have deviations from a Bunch-Davis vacuum. For example, if you consider your mode function to include both positive and negative frequency functions, then you would get other poles. But if you stick to Bunch-Davis, this is the only thing you can have.
Can I ask a question?
Yes, please.
So if I deviate from Bunch-Davis, would the value of P still be the same as what you gave before?
I did not pursue that, so I'm not sure. I would think yes, because I obtained the value of P by only looking at the amplitude. I'm not sure. That's a good question. I didn't try to derive it.
But sorry, Enrico, if you deviate from Bunch-Davis, won't you have also folded? Won't you have to enlarge your set of possibilities to account for folded?
Absolutely, yes. Yeah, no, you do get that, but I'm trying to understand my dimensional analysis argument to derive P. Okay, the quick answer is that I don't know. I have to think about it 5 minutes. That's a good question.
Okay.
In the following, I'll assume Bunch-Davis. Thanks, Merdad, for the good question. Rule number 6 is the soft theorems that we mentioned before. So when you take a soft scalar, then the bispectrum has to obey a certain relation. And when you take a soft tensor, there is another relation. And this relation fixes the numerical coefficient that we had before and leads a unique answer. And that's how you get the result. Notice for the few or perhaps many soft theorem aficionados in the audience, 2 technical aspects that the non-aficionados can completely neglect. One, that I'm always going to take the symmetric soft limit, in which I distribute a little bit of the soft mode on the 2 hard modes. This ensures that the next to leading order in the soft limit vanishes automatically. 2, notice that the soft limit is very simple in terms of elementary symmetric polynomial. It is just E3 going to 0. So that's going to make it easy to take in the following formula. Okay, sometimes an example is worth 1,000 words. So the simplest example turns out to be the bispectrum of gravitons, which was originally derived by Maldacena, now 20 years ago almost, and then re-derived by Guy, Pimentel, and Maldacena using the Sitter isometries. And here we re-derive it using this Boostless Bootstrap Rules. The starting point is the amplitude. It's a well-known 3 graviton amplitude. You can obtain it by just writing the spin-or-helicity expression. But for technical reasons that I'm happy to discuss if you want me to, I'll proceed using polarization tensors rather than spin-or-helicity variables. So this amplitude, it goes like t squared, and t is something linear in momenta, so it has 2 k's, and so it's quadratic in derivatives. And so if you have 2 derivatives, you should make an answer with p equals 2. So you make this answer, which is the bottom line. So the answer is the amplitude divided by kt squared, E3 cube, and then the most generic polynomial of degree 3, so that the whole thing is 1 over k to the 6th, as it should be. And so that there are only 3 possible terms that you can write in that polynomial: E3, kt E2, and kt cube. And each one of them should have a coefficient. The coefficient of E3 is fixed by the normalization of the amplitude. So I only have 2 free coefficients, C1 and C3. There's nothing else that I can write down, which is compatible with the first 5 Bootstrap rules. And now, lo and behold, these 2 coefficients are going to be fixed by the soft theorems. I know what happens when I take a soft graviton, and I get 2 constraints, the leading order one and the next to leading order one. 2 constraints, 2 variables, the solution is unique. C1 is 1 and C3 is -1. And this is indeed the result obtained by Maldacena 20 years ago from explicit calculation. With all the factors of 2, with all the plus and all the minuses. This is exactly the result. There's no fudging.
So you didn't impose the Sitter symmetry.
I did not.
Is it because, yeah, is it automatic? Was it, I'm
no,
just confused.
Yes, I can tell you where it comes from. It comes from having chosen the amplitude to be a local Lorentz invariant amplitude. Okay. I could choose a non-Lorentz invariant amplitude, for example, from interaction, which is gamma dot cube, and then I would have gotten a different bispectrum, which indeed can be generated by coupling of gravity to the inflaton background, and it does appear in the effective field theory of inflation, but it requires a breaking of boosts. So here I'm only deriving, if I The idea is that you start from a Lorentz invariant amplitude, you get the boost invariant bispectrum. But you might as well start with any amplitude, and then you get all the possible bispectra. And I'll comment on this more in detail. In fact, there is a nice talk by Giovanni Cabas on the pre-recorded YouTube channel in which he derives all of this non-boost invariant bispectra, and I think they can all be derived using the same technique as here by starting from boostless amplitudes, which myself, Jakub Suppel, and David Stefanizin recently derived in a paper called Boostless Amplitudes. I'll comment on that in a second. There is another example which is exactly the same, which is the gamma zeta zeta. You write down the amplitude. From the amplitude, the bispectrum has only 2 parameters. You take the soft graviton theorem. There are 2 equations. The solution is unique, and the result is exactly what Maldacena had, down to the factor of 2 and the plus and the minus, just the correct one. So a more interesting example is the scalar bispectrum, since that's by far the most phenomenologically relevant of all. And so here we come to Guy's question. You might start with Lorentz invariant amplitudes or Lorentz breaking amplitudes. Lorentz breaking amplitudes were studied systematically by us early this year. And for 3 scalars, the most generic 3-particle amplitude that breaks boosts is a polynomial in these 2 variables, where e's are the energies and should be identified with k's when you go to the correlator. And so now I can rederive either the boost invariant bispectrum if I want, or all the infinitely many bispectra in the EFT of inflation, just by choosing which amplitude I start from. I'll go directly to the EFT of inflation bispectra because I don't have much time, but if someone wants to see how to rederive Maldacena, I'll be happy to comment on that, and that's where the log appears. Please do ask me later if you want me to show those slides. So let's consider the boost breaking. So it is commonly done. We can start at the lowest interesting ordering derivative, in which we have 1 derivative per field. It's bispectrum, so 3 fields, so 3 derivatives. So the only amplitude that you can write down with 3 derivatives is E1 times E2 times E3, which is what we were calling E3 so far. So you write the most generic ansatz, where the denominator has KT cube, because there are 3 derivatives, and this ansatz has 7 parameters. The one that is in front of E3 square has to be whatever coefficient is in front of the amplitude. Let's call that G, whatever. It's some coupling constant. On the other hand, what I'm calling C0 prime, E2 cube, if you take the KT to 0 limit of that term, it gives you a non-local amplitude, an amplitude with inverse derivatives. If you want to stick to local theories, you should set that to 0. So locality takes away 1 parameter. Finally, you should impose the soft theorems, standard Maldacena, that removes 1 other parameter, and you're down to 5. And that's actually the right result. So this, I claim, with these 5 free parameters, is the result for the bispectrum in a P of X theory, or in the EFT of inflation to leading order in derivatives. And the 5 parameters are nothing but linear combinations of the well-known FNL equilateral, FNL orthogonal, epsilon, eta, and S, which in some sense are free parameters. So you can get exactly the result.
Sorry, can I ask a small question?
Yes.
So it looks like the thing you're calling C0 would also have a non-local amplitude, but it'll have like a 1 over K total instead of 1 over K total cubed pole. So is that what the difference is?
No, the K total is not in the amplitude.
Okay, then it looks like the C0 term it'll go like 1 over K total times something non-local.
This is the formula. Look, so when B is equal to 1 over E3 squared, KT to the P. So if you want to get the amplitude from B, you should multiply times KT to the P, which removes the K total pole completely.
I see. So you only constrain the 1 over K total cubed piece.
Exactly. That's correct.
I see.
But notice that here it's 1 over K squared, product of K squared, that's E3 squared. So when I multiply here times E3 squared, you see it doesn't cancel all the E3s that are in the denominator unless I have an E3 in the numerator. And that's why the C0 prime has to vanish. While C0
I see. Thanks.
Very good question, thanks. And in fact, it's so easy that you can write down the bispectrum to all orders in the derivatives in the EFT of inflation in just one go. You choose how many derivatives you want to include. 72 derivatives, fine. The bispectrum is a polynomial of degree 72 plus 3. You write down the most generic one in these variables with 3 coefficients, and then you impose 2 constraints. 1, the subtheorem. 2, that the highest KT pole, the factor has to include at least one E3, so it's local. If you don't do that, you have a non-local interaction, which you might like or not. The idea now is that we can do this also for all spinning correlators. We write down all the non-boost invariant correlators of the graviton by taking the boostless amplitudes that we recently derived in flat space and going through this game again. And this leads to some, can reproduce in a, I think, rather simple way, some of the interesting aspects that have been noticed, for example, by Creminelli et al., that the graviton bispectrum is unchanged to leading order in derivative. It just comes from the fact that there is nothing else that you could write down at order p equals 2. It's unique. So you don't have to go through the field redefinition, you just see it coming from these rules. Okay, so far we have discussed the bispectrum, and it seems we have made quite some progress without invoking boost. What about higher point functions?
Sorry, can I ask a question?
Yes.
Before moving to the new stuff. So
Absolutely.
you mentioned something about the Lorentz symmetry of the amplitude. I guess I didn't fully grasp it. So when you say Lorentz symmetry of the amplitude, it's the full 4D Lorentz symmetry, right?
Yes, correct.
And in the case of 3 scalars, such a Lorentz symmetric result does not exist. Is that correct?
It's just as constant.
Or it would be just a constant?
Yes, G phi cube, yeah, lambda phi cube.
And then you...
and then you can do it, you can play the game of deriving the Lorentz invariant amplitude, which I do in these extra slides. And I can show you what comes out if you want. It comes out the epsilon to 0 limit of Maldacena, including all subleading slow roll corrections.
But it has some relation to your theorem, or not?
Yes, because you recognize that this constant should be interpreted as V cube, because it's the coefficient of phi cube, which can be written as eta dot, as in this slide. And so you can see
so I should set it to 0 under the assumption of the theorem.
If you want to go back to the theorem, and yes, and insist that you neglect all the slow roll things, yes. But here I'm actually capturing all the slow roll coefficient as well.
Okay.
Yes, very good. And here you can rederive what we call the conformal limit of inflation, which is the one you would get from starting from a Lorentz invariant amplitude. And it's proportional to eta and eta dot as it should be. So if you throw out slow roll, then it's 0.
Okay.
Very good, thanks. Okay, good. New topic. So we need like more power. These rules are not enough to go to 4-point functions. And so what we derive here are the generic consequences of unitary time evolution on the boundary correlators. So you might complain that so far it was all simple because it was contact, and so now I'm going to provide some more ammunition to tackle correlators that have exchange diagrams that are much more complicated. There was a detailed derivation of this cosmological optical theorem that I'll discuss in a second in Harry Goodhue's talk on YouTube. I refer you to that for a derivation, so here I'll just discuss the result. So unitarity is one of the pillars of our understanding of physics through quantum field theory. And it's well understood, its consequences are well understood for amplitudes, for example, the optical theorem or cutting rules. But it is not clear how the unitarity of time evolution is encoded on an object which lives on the boundary, which has only spatial correlations. And that's something that I heard Nima emphasizing many, many times in his recent talks. So here we're going to provide that consequences of unitary time evolution on the boundary that do not mention the time evolution. They're just relations on the boundary. And the best way to express those results is to forget about correlators and phrase our results in terms of the coefficient of the wave function of the universe on the boundary. So I'm going to call those coefficient psi-n. For the bispectrum, psi3 is simply related to the bispectrum, but for a higher point function, the relation is slightly more involved, but not very much. Okay, so we start from u dagger equals 1, as you might suspect, to find the consequences of unitarity. And by using the analytic structure of the Sitter mode functions, we are able, for all three-level contact diagram, to derive this relation on the coefficient psi-n of the wave function. So you take the psi-n coefficient, you sum its complex conjugate, but evaluated at minus Ka. So wherever you see the norm of K, you should put a minus in front. And that should be 0. This expression can be extended to the whole lower half complex plane by an appropriate analytic continuation of the wave function that we provide in the paper. And this has to be 0. So this is the consequences of unitarity for contact diagrams. Some simple, but actually it has some interesting some interesting consequences. First of all, you should think of this as the cosmological equivalent of Hermitian analyticity for amplitudes. You can rewrite this expression as a relation on the negative imaginary axis between the real part of psi and the discontinuity of psi. That relation might not be as useful as for amplitudes because there you expect not to have any discontinuity. And so this just tells you real psi is equal to 0. But it has many consequences for correlators. For example, for all IR finite correlators of massless scalars, the wave function has to be real because this expression is just real, imaginary particles 0. For all IR finite correlators with any number of conformally coupled fields, the wave function has to be either real or imaginary, depending if you put an even or an odd number of conformally coupled fields. So in particular, if you take any correlator with an odd number of conformally coupled fields with any interactions, that's 0. The correlator is 0 because the correlator is the real part of the wave function. And this is a consequence of unitarity. Unitarity has even more far-reaching consequences when you look at IR divergent diagrams. As we mentioned before, you can have logs. Perhaps the simplest one of these logs is the one that you get for phi cube interactions in the Sitter. And you can directly compute the wave function. This is the expression that you get. Notice that now, when I take the log and I evaluate it at minus its argument, I get an I. So I've introduced some branch points and branch cuts. And that I has to cancel exactly the terms that are in the wave function given by this expression. And indeed, you find that the logarithmic divergent part of the real wave function are related to the non-logarithmic divergent one of the imaginary part of the wave function. So the two are tied together. So all of these I pi's that appear here, you can see that their coefficient is precisely the prefactor of the log, down to the factor of 3. And this had to be by unitarity. Things get even more exciting when you consider exchange diagrams. And here we studied specifically 4-point exchange diagrams. So if we define by analogy with the Mandelstam variable S to be the norm of K1 vector plus K2 vector, then our cosmological optical theorem implies the following relation, that the psi4 plus its conjugate evaluated at minus the energies has to be written in terms of 3-point functions by these expressions. Here, this expression that we have written is valid for the S channel, but you can easily sum on both sides on all channels and get a more generic expression. This is very powerful. This determines all the singularities of psi4. Because note, it tells you that the singularity of psi4 are going to be what you would call the K total singularity of psi3, but now the argument is funny. It's like K1, K2S, K1, K2 minus S, K3, K4S, etc. So the singularities of psi4 are fixed by the singularities of psi3 by this relation, which is very powerful.
Sorry, but you missed the K total singularity of psi4, right? Because it cancels between the two.
Exactly, that's the power of the thing. It has to cancel precisely, and it does.
Okay, but I'm just disputing the fact that you know all the singularities.
Sorry, all the singularity except for one.
Yes.
that we already derived before, yes. Partially, that's the reason why we derived the other singularity in the paper in such a detail, so that we can claim that we discuss all the singularities in the paper. You're right. In fact, that cancellation is not trivial, because there is, the right-hand side doesn't even know about k total here, the k total 4. So how can this be true? And yeah, it is. It cancels. If it's easy to rewrite this in terms of a relation between the trispectrum and the bispectrum. So this is really getting to kind of useful for phenomenology. If you want to compute the bispectrum, you can try to, you will be able to bootstrap it from this relation if you know the bispectrum that appears on its vertices. So it's pretty straightforward to see that this uniquely fixes the trispectrum up to contact terms. So all the
Enrico, could I ask something?
Yes.
Because in the case of amplitudes, you actually you need kind of a dispersion relation to get the real part of the of the 4-point function. So how? I mean, here also you're only getting the real part. So the full, how do you get the full 4-point function from this relation without the dispersion?
Yeah, very good question. So the way, so we have done it only for one relation, but I'm going to tell you why I believe it works for all of them. Well, we have done it to bootstrap it. We did it for the trispectrum in the EFT of inflation from pi dot cube as individual vertices. And then you can write down a bunch of free coefficients of what you expect it to look like, and they're all fixed by this, all of them. But more generally, you can say, well, let's suppose it's not fixed. So suppose that there are two solutions of these equations for some fixed bispectrum. There are two trispectrum. Then the difference, you can prove that it obeys this equation where the right-hand side is 0. Mm-hmm. So you can only, you predict it up to things that obey an equation, and the equation is what says that they are contact interactions. So the difference between two solutions of these equations is a contact interaction. So in that sense, we can rederive everything up to contact interaction. That's the argument in general.
I see. Because for gravity, for example, these contact interactions are probably the hardest. So there's
contact interaction here, I believe that should be pretty easy in terms of the Bootstrap rules that I set down before. Because I don't think that there are any other things that we are missing. You write down the amplitude, you multiply it times whatever polynomial of the appropriate degree, and the coefficient of this are either fixed by soft theorems or free parameters. I cannot see how I'm missing something. But
the poles are getting much higher, and so you get much more of these terms.
That's true, but that just means that there are many quartic interactions in the Lagrangian. Mm-hmm. And that's just the way it is.
Yeah, can I add maybe one comment to Enrico? So this is, I guess, mirrors the bootstrap for scalars in even flat space, that you can construct the 4 particle amplitudes up to contact terms, right? So we cannot say anything about the EFT part, the part that is analytic in ST and U.
Sure. Yeah.
Oh, sorry, can I ask, so when you have exchanges of massless particles, the separation between exchange and contact is not quite so sharp anymore? Because by changing gauges in the propagator, I can shuffle things back and forth. So how do you envision taking care of that?
So you're talking about some unphysical bulk gauge dependent statement, and you're saying, how is that encoded?
For example, consider graviton Compton scattering. So what you call exchange and contact kind of depends upon what gauge you pick. So the sum of the two things is kind of well defined.
Yeah, and that calculation is not clear to me, but here is very clear. If the right-hand side of this expression is 0, that's contact. If it's not 0, that's exchange. That's my definition on the boundary. And I think that's unique. Mm-hmm. That's how I would define it. Okay. And it might be that in the bulk, this has different avatars because of gauge redundancies. So you see contact was here, and that there is basically 0 on the right-hand side. And so if it is not 0, then I call it exchange. Very good, yeah. Okay, I'll keep So sorry, I want to get to my summary, and then maybe we get back to discussing these issues. Oh, we also checked that this works for the graviton exchange trispectrum in canonical single field inflation, as computed some 12 years ago. And it works. This relation, it works both for exchange of scalars and for exchange of spin to massless particles. Okay, finally, let me get to the summary. So the goal here was to understand observables as what we measure, which is the future limit of correlators or of wave function coefficients. And I want to do that for cosmology. So I want to do it around the sitter, but without assuming the sitter boost. So it's phenomenologically more useful. So I call that a boostless bootstrap. I could do it for the bispectrum using a set of rules that I think make quite transparent the consequences of some of our choices, like a Bunch-Davies or Lorentz invariance and locality. And both it reproduces known results, it also extends to all possible orders in derivatives. And to go beyond the bispectrum, I think unitarity is the key player, and therefore we derive this cosmological optical theorem, which we believe should fix 4-point function in terms of 3-point functions up to contact interactions. So I'll stop here, and thank you very much for listening.
All right, let's unmute ourselves and give Enrico a round of applause. All right, questions, you can unmute yourself and ask.
Can I ask one question?
Go ahead.
Yeah, so I was wondering about the loop diagram. Can you say something about using the optical theorem for the loop diagram?
Yeah, excellent question. Perhaps I'll let also, I'll say a couple of words, and maybe my collaborator, Harry Goodhue, want to say something about it. So we were able to derive also a no, I got confused about some other poles that we, so what we extended to the loop level was the study of the k-total poles. In terms of loops, no, I don't think that the current derivation does not assume loops. This is I think one can try to do the same derivation similarly for loops, but we haven't done it. So this does not apply to loops.
Okay.
Could I ask a question?
Yeah.
So how is it that you get from this right-hand side, this factorized product of 3-point functions, what you said fixes up the contact terms? So, you know, I have in mind conformally coupled scalars exchanging a conformally coupled scalar. I played with this example, checked your result that it works, but it's not clear to me how you could go from that to get the full 4-point function.
Yeah, very good. So great to hear that you checked it and it works, because for the external being conformally coupled, that one we didn't check. Okay. But you have to write down an ansatz for what you expect. And your ansatz need to have a certain pole structure, certain set of singularities. It's going to be some k-total singularity, what we call E left and E right singularity, which would correspond to the E total of the individual diagram. And you should, that fixes the denominator, and then the numerator is going to be fixed, going to be the most generic polynomial with free coefficients. And then you feed that into the formula, and that gives you, surprisingly, a large number of constraints, because these coefficients are just numerical. So you should find a numerical solution for each one of them. And for the one we played with, that fixed all the coefficients. And the argument that I gave before suggests that that should work in general. Now, you have to be a little bit clever to come up with the right answers at the beginning. It has to have the right number of coefficients. It needs to be generic enough. So that's going to be the next step. And we started playing with it, but we haven't done it only for this pi dot cube in the EFT of inflation trispectrum. And there it worked. But
yeah, probably I can add a quick comment to that. I think what Aaron is probably mostly interested in are cases in which the trispectrum might have locked singularities, like are infinite. So I think that in those cases, you have to also make it a little bit more rigorous what you mean by this analytical continuation by sending k to minus k. So we didn't do this for the 4-point function. We did it for contact terms, but I think that is like part of the problem that has to be understood better.
Yeah, I mean, these are transcendental
Exactly.
functions, and so the full answer is not factorized, but the right hand side is manifestly factorized, and
yeah,
so it's trickier.
Yes, in the 3-point function you have a log, and in the 4-point function you have double log. I don't know what you call it in your work. I forgot. Yeah, for those cases, physical structure is more involved than the cases Enrico was talking about, like trispectrum in EFT of inflation. So I think that is like a next hurdle.
But Sata, correct me if I'm wrong. At the level of the equation, you see that it works because on the left-hand side, you see a cancellation at the level of the integrand from the propagators that makes it factorized.
Yeah, so I believe that the similar equation would hold. It's just that to bootstrap it, you have to like understand how to approach the branch cut from below or above. So it's a little bit unclear to me how we should do that.
Yeah, I'm sorry. I had in mind a bunch of polynomials, which are clearly much simpler than what we had in mind. But
yeah, I have no reason to think it doesn't work, but I think that there might be a different sort of loss of information, or making an ansatz at least sounds it sounds different in this circumstance. But
yeah, you're right. We have to educate ourselves what is the ansatz. My general view is that it might look like we have some big principle behind writing down a Lagrangian, but actually it's just a Taylor expansion in which you write down all possible terms compatible with a set of symmetries. So it seems to me you should be able to do exactly the same at the level of the result, write down all possible terms compatible with some symmetries, and there has to be a reason why certain terms appear or don't. To that extent, I'm optimistic. Certain constraints, physical one like locality or unitarity, might be easier to see either in the Lagrangian or in the observable level, and that depends, and we still have to prove that. But it seems it's morally should work.
Okay, thank you.
Sorry.
Go ahead.
Yeah, so with the optical theorem, do you have any thoughts about maybe deriving something like a on-shell recursion relation, much like in the spirits of BCFW, that type of relations in scattering amplitude program?
Yeah, that's definitely in our mind, and that's definitely the hope, but we just finished understanding this. I think that we made some progress in understanding the analytic structure that wasn't clear to me of this wave function coefficient, and that might help. It's slightly different from amplitude. We emphasize analytic continuation to the lower half complex plane rather than the full plane, so we have to work a little bit harder to get all the way to recursion relation, but this should be definitely in the background of everyone's mind. So I don't have a better answer than that at the moment.
And one more question, like so we had like a bunch of these like rules that you stated. Like, do you need all of those rules, or like does one rule imply the other? Like, can you like you know?
No, I really hope that. No, I think I need them all. So far I haven't. Yeah, I think I need them all.
Okay.
I think you can see in the derivation how I use them one by one. So I think I need them all, and I think I don't need any more.
Okay.
With one exception that I'm happy to mention, but I think I need them all, and they should be enough.
Okay.
For massless scalars and tensors.
What is the exception?
Maybe we punt that to later. I'll write it down, and I will not forget to mention it later. Any more questions?
Can I ask a question?
Yeah, go ahead.
I have a question about linear mixing. If you break boost symmetry, there appear mixing between particles with different mass and spin. Can you apply your technique to this type of system? So for example, you can think about quasi symbol field inflation.
Yeah, so okay, so there are two things. First of all, the bispectrum, the boostless bispectrum bootstrap that I did was all massless stuff. So there, the linear mixing.
Yeah, the dispersion relation changed a lot. So I think the problem will be more complicated.
But there I did only massless stuff. So indeed, if
okay. So you can add that.
Those don't apply, and you have to work a little bit harder. I think it would be interesting to see what happens. I would expect the rules to be more complicated just by looking at the answer. By looking at for a single field, the answer is not a simple result. So here, my starting point was that if you look at Maldacena bispectra, they're all very simple. So you would expect that there is a simple set of rules. For quasi-single field, it's much trickier, but maybe working hard, one can find some simpler way to write that result. I don't know, good question.
Okay, thanks.
Let me, before wrapping up, let me abuse my power as chair and ask a quick question, Enrico. And then if you think it's long answer, you punt. Like a nice thing about the EFT of inflation is that it ties up, right? Operators at different orders. So you dial the speed of sound and you see that it enhances non-Gaussianity and so on. Do you think, so now you derived all of these by spectra. So in principle, you derived without writing the Lagrangian, everything that the EFT of inflation could give you, modulo this no linear linking, right, between different shapes. Do you think you can see that also from the bootstrap, or?
Yeah, excellent question. I think that is the major shortcoming of what I'm doing, is that I can only tell you there are 5 parameters, but 2 of them can be extremely large, like FNL equilateral, FNL orthogonal, 1 over CR squared, and 3 of them cannot because they're epsilon or eta, stuff like that, that if it is large, it screws up the whole thing. Because I haven't told the bootstrap yet that there is this approximate shift symmetry and a linear evolution, and a combination of that is unbroken. So I think one should be able to do what you say and derive these relations, but I have not done it. And I would be very interested in doing it because it's clearly the important question. Which one of these coefficients can be arbitrarily large and which one cannot?
All right, great. Well, thank you very much. I suggest we take a 5-minute break and then we carry on with the discussion.